Section 18. Forces and Free-Body Diagrams. The essential question: how do you determine the size and direction of individual forces and delta E overall? Do you remember what delta E stands for? If you said change in energy, you've done a good job. Let us enhance our definition of force. First point: forces are any interaction or contact between two objects. During contact, the same amount of force acts on each object, but the objects are pushed or pulled in opposite directions. Here we see force on B by A and force on A by B. These forces alone could cause each object to move, but what we will see is that if you added these forces together, the total amount of force, or momentum change, is conserved. Fascinating. Here are some more examples. Here we see two skaters. It doesn't matter who does the pushing. The force is the same on both of the skaters. One is pushed left, and the other is pushed right. But I wonder, how do we determine whose motion is changed more? You should explore this answer later. In our other example, we see an apple falling to the earth. But did you also know that the earth falls up to the apple? But why don't we see that? Curious. We'll have to explore that further as well. But there are more forces at play than just gravity. We will learn about 4 other forces in addition, and you should become familiar with how each of them works and affects other objects. Let's take a look at them, shall we? Gravity affects 2 objects that have mass. A small force of gravity would be 2 peanuts pulling on each other in space. A large gravitational force would be 2 stars struggling against their epic masses. The normal force is when 2 objects simply come into contact with each other. A small normal force might be a high five, but a large normal force could be an elephant pushing down on the earth with its epic mass. Electricity. This is when 2 objects which have a charge of positive or negative pull or push against each other. The smallest of this force might be 2 electrons pushing each other through a circuit, where a large force might be a sock given a huge amount of static electric charge pulled from a dryer and now clinging on to your sweater for dear life. Friction is with 2 objects rubbing against each other. A small example of friction would be the force of friction slowing down a piece of ice sliding across your desk. But a larger force would be your knees scraping mercilessly upon the carpet, causing burns. Another force is tension. This is where 2 objects are connected by a string or rope. There is a pull between them, much like a yo-yo and your hand as a small example. But a large tensional force would come from a crane lifting a piano high into the sky. So, how do we show these forces? We use the three-body diagram. Let me show you. A three-body diagram is a picture of an object, or a collection of objects, and the forces that act upon that object or the system of objects. We use them to quickly see if the forces are balanced or unbalanced, so we can tell if the energy of the system is changing or not changing. This is a big important deal. It allows us to explain the past and predict the future. Let us look at an example. When you draw an object, that object is represented by a simple box. You can label the box if you choose, but no longer are complicated illustrations required for representing objects in reality. So this ostrich becomes this ostrich. A force is represented by arrows that show the direction in which the force is acting. What direction is it trying to change the motion of the object? In this case, gravity is trying to change the motion of the ostrich downward toward the center of the earth. But this ostrich is not falling down, so there must be a force balancing it. What force could that be? It is the normal force, and we will find that it will be equal and opposite to the force of gravity, and that is why we know the motion of the ostrich is not changing relative to the ground. We use these diagonal slashes to represent equality and symmetry between forces. Them being equal and opposite, if you added them together, would equal 0. And so we say sigma F is 0. And we can also say that the change in energy is 0. There is no new energy being added to or removed from the system. Let us look at another example, and in this case, the forces will be unbalanced. Bryce Harper, legend of baseball. He is the Sultan of the Slide, the Baron of the Bat, the Thane of the Throw. We will use his greatness as an example of drawing a free body diagram. But first, we must convert him to Bryce Harper, box. Now let's examine what forces are acting upon Bryce Harper the box. First, he is upon Earth, and gravity will be pulling down upon him. But he is not falling into oblivion. No, he is held up by the normal force of the ground. His momentum is forward towards the base, but he will not slide forever. No, he is slowed down and will be eventually pulled to a stop, his energy changing, decreasing. by the force of friction from the dirt. Yes, he is unbalanced, and his momentum and his energy is being changed over time. So now we must revisit the essential question. How can we determine the size and direction of individual forces and the change in energy overall? The answer is we can represent the system or object using a free body diagram. We can then analyze the object and identify any forces acting upon it. We can then look and see which forces are equal and opposite, canceling each other, and see if the overall system is gaining energy or losing energy based upon the sigma of all forces present on the diagram. Good luck.